This is lesson 2.6, special factors. Now that we know how to factor using common factors, and we can factor any regular trinomial, the last thing we're going to learn is two special types of polynomials that can be factored very easily. We call these special factors. The first is called difference of squares, and the second is a perfect square trinomial. A difference of squares is when two perfect squares are being subtracted. So this is a unique situation that can be factored in a really simple way. Reminder that a perfect square is anything that can be square rooted. So here I have a list of the perfect squares. Those go on forever, but here are a couple of them. These are perfect squares because you can take square roots of each of them. So the square root of 9 is 3, square root of 25 is 5, etc. But x to the 2, x to the 4, x to the 6, etc., those are all perfect squares as well because they can be square rooted. Reminder that x squared is just x times x. So the square root of x squared, well, you're taking something and you're squaring it and then you're square rooting it. So those actions cancel each other out. It just leaves you with x. Same thing if you had x to the power of 4. The square root of that would be x squared because x squared times x squared gives you x to the 4. So all like numbers and variables can be perfect squares. So this right here is something you're going to have to memorize that represents the difference of squares. This is what it looks like, and this is how it gets factored. In this case, A and B represent perfect squares. So when you're factoring, the two brackets that you'll get are identical except for the signs, which are different. So one will have a positive sign, one will have a negative sign. It doesn't matter which one goes where, as long as you have one of each. The reason this has to work out is when you expand these brackets out, the middle term has to be eliminated. That's why we're left with just a binomial. Most of the time we have, like maybe, for example, we have this. That's a trinomial. We have 3 different terms, and we know how to factor that. But with difference of squares, we only have 2 terms. And so this looks a little more tricky to factor, but it's just because that middle x term has been canceled out because these are different signs. To figure out what the A and B are, like what values go into your brackets, the first term in each bracket is whatever the square root of the first term here is. And the second term in each bracket is the square root of the second term in your original question. We'll look at a couple examples to make sure this makes more sense. But reminder, when we're factoring, always take common factors out first. And sometimes there are situations where they are not factorable. Let's do this example first. We've got x squared minus 81. We want to factor it. This doesn't look like what we're used to. It's not a typical trinomial. There's no common factoring we can do. How do we factor it? We want to be able to identify that this is a difference of squares. We know it's a difference of squares because x squared is a perfect square. It can be square rooted. And same with 81. The square root of that is 9. And these are separated by a subtraction sign. So now that we've identified it as a difference of squares, we can factor it instantly because we'll just have our 2 brackets. They're going to be identical except for different signs. The first term in each will be the square root of the first term, which would be x. And then the second term in each is going to be the square root of the second term, which is 9. And as I said, one sign's positive, one sign's negative. I did a check here just to show you why the difference of squares works. If we were to expand these brackets out, we would get x squared minus 9x plus 9x minus 81. This is why that middle term goes away, because you have minus 9x plus 9x. Doesn't matter what it actually is. It's going to be canceled out because these signs are different and everything else is identical. This example is a little more complicated. We need to factor this, so let's identify if it's a difference of squares. The first term, this is a perfect square because the coefficient 9, that's a perfect square, and x squared can also be square rooted. So that's good. And 64 is also a perfect square. The square root of that is 8. It's separated by a subtraction sign, so we know it's a difference of squares. The first term in each is going to be the square root of this. The square root of 9x squared is whatever the square root of 9 is, whatever the square root of x squared is. Forgot my square there. So that leaves us with 3x. So The first term in each bracket is 3x, and the second term in each bracket is 8. And one is a minus sign and one is a addition sign. In example C, 20 and 5, those are not perfect squares. So right away, this is not a difference of squares. But remember, we have to take out a common factor first. And the common factor here is 5. Remove that common factor, we're left with a difference of squares because 4 and 1 are perfect squares and x squared and y squared are perfect squares. So then we set up our two brackets. They're going to be identical except for different signs. The first term will be 2x because that's the square root of this first term. And the second term will be y because that's the square root of the second term. A couple more examples, I'll go a bit faster. In this case, it doesn't matter that the variable one comes second. We know it's a difference of squares because this is a perfect square and this is a perfect square. So the first term in each will be 5 because the square root of 25 is 5. And the second term in each bracket is going to be 4x squared because, which I've shown here, 4x squared times 4x squared is 16x to the 4. We've got a plus and a minus. A common mistake people make is they look at this, they identify that this is a perfect square, this is a perfect square, so it must be good, we can go ahead with it. But this is not a difference of squares because this is addition, not subtraction. So this is not factorable. We can't do anything else with this. We leave it as it is. And then in this example, yeah, it's not a perfect square right away. We got to get rid of this common factor of 2. This is a perfect square, but this one is not. Once we take out our common factor of 2, this 8 is not a perfect square. So this is as far as you can factor. You've done your common factor, there's nothing else you can do. So sometimes it might look like it could be a difference of squares, but make sure you check that each of these terms is a perfect square. The second type of special factor is called a perfect square trinomial. A trinomial that is the square of a binomial is called this perfect square trinomial. How you identify it is in your trinomial, the first and the last terms are perfect squares. And the middle term, this is something you're just going to have to memorize, the middle term is 2 times the square root of the first term times the square root of the second term. So example here, this is a perfect square trinomial because x squared and 16 are both perfect squares. And then the middle term, 8x, is equal to 2 times the square root of the first term times the square root of the second term. 2 times x times 4 gives you 8x. So it's a bit more work to identify if something's a perfect square trinomial, but that's how you do it. Depending on the sign of the middle term, there's 2 different ways to factor perfect square trinomials, which are shown here. Either you're going to have a positive sign or a negative sign. It looks pretty similar to a difference of squares. You have like your a and b is the same in each, but the difference is that for the difference of squares, you have a positive and a negative. And for the perfect square trinomial, you either have both positives or you have both negatives. So your final answer will look like this, because if you have the same factor repeated twice, you just write it as that factor squared. And how you can tell what sign goes here is what's the sign of the middle term. So when the middle term is positive, the sign is positive. When the middle term is negative, the sign is negative. Some examples will help solidify this. So we want to identify if each polynomial is a perfect square trinomial. If so, factor it. If not, leave it. In this first example, so we want to check that the first term and that the last term are perfect squares. In this case, that's pretty easy. Yep, we're good. The middle term is a little bit more work. We want to figure out what is 2 times the square root of the first term times the square root of the second term. It's 2x5, 10x. Yes, we're good to go. This is a perfect square trinomial. So now it's super easy to factor because it's just going to be one bracket squared, where the first term is the square root of the first term here, and the second term is the square root of the last term there. Then I know it's going to be a positive sign because the middle term here is positive. In this example, we ought to check if it's a perfect square trinomial first. If it is, we can factor very easily. This and this are both perfect squares, so we're good there. And then for the middle term, we want to calculate what is 2 times the square root of the first term times the square root of the last term. 2 times y times 3 gives us 6y. We're good to go. It is the middle term. We know it's a perfect square trinomial, so it's just going to be a bracket squared. First term is the first term square rooted. Last term, or sorry, the second term here is the last term square rooted, so 3. And then we know it's going to be negative. 6y is negative here. This example, same idea. The first term and the last term are both perfect squares, so that's good. The middle term we check 2 times the square root of the first term times the square root of the last term. That works out. It gives us our 12x, so we can go ahead and factor very easily here. The first term is 2x because it's the square root of this. The second term is 3 because it's the square root of this. And then we have a negative sign because our middle term is negative. So you can see that once you are able to identify these patterns, it makes factoring very easy. 2 more examples. In this one, yeah, the first and the last terms are perfect squares. That checks it off. But the middle term doesn't work out. Because if we try to calculate this, 2 times the square root of the first term times the square root of the last term doesn't give us that middle term. So it's not a perfect square trinomial. In this question, we're going to leave it as is. And in fact, I don't believe this one is factorable. So we just leave it as it is. Very last example with a check here. Yes, it's a perfect square trinomial because this can be square rooted and this can be square rooted. And then we check the middle term here, which we've done here. So once we've identified that, it makes it easy to factor. We've got our first and our second term based on the square roots of these terms. And then it's a negative sign because we've got a negative here. It's okay that there's multiple variables. We do it the same way. And then I've shown a check over here. Again, when we're checking our factoring, just multiply it out using the stuff we learned in 2.2, and then check that you get your original question. So those are the special factors. It's nice because even if you forget them, you can probably just still factor them anyways. But if you can remember them, then it makes your life a lot easier because you can factor very quickly.